And just to complete that then, I just tidied that up a bit. The inverse of a to the minus 1, is equal to minus 2/3 minus 1 and 1/3, oops, 1/3, plus 1 minus 2/3, minus 11 over minus 3 is plus 3 and 2/3. Um, 6 over minus 3 is minus 2. Plus 1, minus 2, and plus 1. Okay, which is minus 0.6 recurring, minus 1.3 recurring, 1, minus 0.6 recurring, 3 and 2/3, or 3.6 recurring, minus 2, 1, minus 2, 1. And there we have it, our inverse of the 3 by 3 matrix A. Okay, and we can then go on to use that, for example, if we have known forces in a system or a structure is equal to a stiffness matrix of the unknown deflections, so the free to move nodes of a structure. Let's say we have a structure that looks something like that with a load Q, and we have a reaction there, so it's fixed, and it's fixed with a roller there, for example. So we've built up a stiffness matrix. This is the stiffness matrix of the degrees of freedom that are free to move. So these 1, 2, 3 degrees of freedom in a 3 by 3 matrix, say, which wouldn't really look like that, but it'd be that 3 by 3. It would be a symmetrical matrix, but we'll come on to that. But an example of where you might need to know the okay, so this is the stiffness matrix, the 3 by 3 matrix of the free to move nodes, and these are the deflections which we don't know under this load here. These this matrix of loads known, we know that this load is known. Let's say that's on degree of freedom 1, 2, and 3. So there's no load on that degree of freedom, no load in that degree of freedom, and a load of, say, 2 in that degree of freedom. So we have a a system of known loads, the stiffnesses, and then these unknown deflections in 1, 2, 3 degrees of freedom. And then for completeness, we'd also have these fixed nodes, fixed degrees of freedom, I should say. Let's draw that way up. So these are fixed, so these have no deflections. So we know the deflections. We also know that the deflections are 0, so these actually cancel out. So we're left with this equation. The force known is the stiffnesses, and the times the deflections unknown. We can rearrange that now because we know what k to the minus 1, so this is the inverse of that matrix, times the known loads will give us the unknown deflections, and then those unknown loads, the reactions, that this reaction here R1, R2 and R3, if we want to find those, we have another system of equations where these are the stiffnesses of the degrees of freedom that are fixed, multiplied by those deflections which are unknown, so the in relation to these unknown deflections, but that's the same. We've actually now calculated those, so we know those, plus the interaction of the fixed nodes times deflections known, but we also know that these deflections are at R3, R2 and R1 for those degrees of freedom. The deflections, because they're fixed points, deflections are 0. So this term cancels out, but we've calculated du using our inverted matrix. We can now work out our unknown forces, which are our reactions R1, R2 and R3, using this stiffness matrix 2, 1 times the unknown deflections which we got from this step here. So that would be a practical use of the inverse of a matrix. We'll come on to look at some examples that use that.